In classical software development programming, what we do is we start with a lot of rules, or what we call programs. We write them using programming languages, and we provide some input to these programs. And these programs process the input and give us some answers, right? So that is how most software is implemented today. But in machine learning, it is a slightly different kind of approach that you take. In machine learning, we know what the input is and we know what the output is going to be, and we expect the computer to figure out an algorithm or a rule or a program to solve that problem, right? So we take a lot of input data, training data, where we have inputs and outputs. We feed them into the machine learning model, and it comes back with a like a trained model, which we can now use to get outputs for new inputs. Okay, so that's like a basic introduction to machine learning. So we'll begin with a brief discussion of the basics of PyTorch and talk about tensors and gradients. Don't worry if you're not familiar with these terms. We are going to cover them in a lot of detail. And as you know, this post is the first in a series of tutorials on building deep learning models with PyTorch. It's an open source neural networks library developed and maintained by Facebook. And this series attempts to make PyTorch a bit more approachable for people starting out with deep learning and neural networks. In this particular notebook, we'll cover the basic building blocks of PyTorch models. So this tutorial takes a code-first approach towards learning PyTorch, and you should try to follow along by running and experimenting with the code yourself. We'll use the Anaconda distribution of Python. So this is a popular distribution used for data science because it comes pre-included with a lot of data science libraries. And we'll use it to install libraries and manage virtual environments. For interactive coding and experimentation, we'll use the Jupyter Notebook platform. Don't worry if you're not familiar with Jupyter, we'll go through it as well. And all the tutorials, all the notebooks in this series are available hosted on Jovian, which is this website. Jovian lets you make Jupyter notebooks shareable, collaborative, commentable, and reproducible. So you can share Jupyter notebooks with a single command directly within Jupyter, and you can let others discuss and comment on specific parts of your notebooks with a commenting interface. And anybody can reproduce your work, including you, with just a single command. So here's what you need to do to get started. So first, you install Anaconda by following these instructions. This is on the conda.io open source project homepage, and under the installation page in the user guide. Depending on the platform you're running, you might have to follow different instructions. In my case, I'm on Mac OS X, so I need to follow these instructions. I already have Conda installed, so I don't need to do this. But what you definitely need to make sure is that you have Conda added to your system path, right? What that means is if you go to your terminal or command prompt and type the command conda, that should give you a set of instructions. Next, we install the Jovian Python library by running the following command. This will allow us to clone the notebooks that you're seeing here and run it on your own machine. So I copy this command, paste it on the terminal, and in my case, I already have it installed. Next, we download the notebook for this tutorial using the Jovian clone command. So the clone command can be found by just clicking the clone button at the top of this page. And that copies the clone command to my clipboard. Now I can paste this command, and this downloads the files. Then I can go inside the folder. And as you can see here, I have two files, a Python Jupyter notebook and a Conda environment file. The next step is to run conda env update. What this does is it looks into the environment.yml file, installs all the required packages, and puts them inside a virtual environment. There it is. To activate this environment, use conda activate 01 PyTorch basics, which is the name of this environment. Now this virtual environment is activated and all our required libraries have been installed. Once the virtual environment is active, we can start Jupyter by running the Jupyter Notebook command. And as you can see here, this opens up a web-based interface on localhost 8888. If it does not open automatically for you, you might need to click this link or copy paste it into the browser. Now you can see that I have the same notebook here, and once I click on it, this will open up the notebook within Jupyter. So now, Jupyter is an interactive computing environment where we can write some text, add some documentation, and we can also have some code cells wherein we can write some code and execute it. The first thing I'm going to do is I'm going to go into the kernel menu and click Restart and Clear Output. What this does is it removes all of these outputs of the existing cells, which have been saved from the last time this notebook was executed. As you can see, all the outputs are now gone. I'm also going to hide the header so that I have more space on the screen. Okay, so now we begin by importing PyTorch. PyTorch is automatically installed because we cloned the notebook using Jovian, and then we installed all the dependencies using Conda. I can run it by pressing the Shift plus Enter or Shift plus Return key. So now that PyTorch is imported, let's talk about tensors. At its core, PyTorch is a library for processing tensors. A tensor is a number, vector, matrix, or any n-dimensional array. Let's create a tensor with a single number. I've created a tensor with the value 4. 4 point is shorthand for 4.0. It is used to indicate to Python and PyTorch that you want to create a floating point number. And we can verify this by checking the dtype attribute of our tensor. So let's try creating a slightly more complex tensor. In this case, I'm creating a vector. If you can see, I have provided a dot with the 1 to indicate that I want a floating point tensor, and then I don't need to provide a dot with the rest of the values. And I have to pass a list of numbers into torch.tensor to create a vector. Similarly, I can provide a list of lists with a fixed structure to create a matrix. What you can also see here is if I try to change the shape where the first row and the second row have 3 elements, but the third one has have 2 elements, but the third one has 3 elements, it's not going to work. So a tensor expects that it has a valid shape. Similarly, you can also create a 3-dimensional array, which is essentially a list of matrices, each of which have the same dimensions, right? So the first element of this array is a matrix with 2 rows and 3 columns, and the second element is also a matrix with 2 rows and 3 columns. Since tensors can have any number of dimensions and different lengths along each dimensions, we can inspect the length along each dimension using the dot shape property of a tensor. So in this case, T1 is just the number 4, T2 is a vector, T3 is a matrix, and T4 is a 3-dimensional array. So T1 has the shape of T1 is just an empty array, and the shape of T2 is an empty array, is an array containing the length of the vector. The shape of T3, the matrix, simply contains the dimensions of the matrix, and similarly for T4. We can combine tensors using the usual arithmetic operations. Let's look at an example. So I'm creating 3 tensors here, x, w, and b. All of them numbers, floating point numbers. W and b also have an additional parameter requires grad set to true. We'll see what it does in just a moment. Let's create a new tensor y by combining these tensors. So I have y which equals w multiplied by x plus b. And as expected, y is a tensor with the value 3 times 4, that's x times w, plus b, that's 5, which is 17. And what makes PyTorch special is that we can automatically compute the derivative of y with respect to the tensors that have requires grad set to true, which are w and b in this case. Right? So to compute the derivatives, we can call the dot backward method on our result y. And the derivatives of y with respect to the input tensors are stored in the dot grad property of the respective tensors. So dy by dx is stored in x dot grad, dy by dw is stored in w dot grad, and dy by db in b dot grad. Let's take a look at their values. And as expected, dy by dw has the same value as x, since y is wx plus b. So it has the value 3, and dy by db has the value 1. Note that x dot grad is 1 because x does not have requires grad set to true. The grad in w dot grad stands for gradient, which is another term for derivative and used mainly when dealing with matrices. NumPy is a popular open source library used for mathematical and scientific computing in Python. It enables efficient operations on large multi-dimensional arrays and has a large ecosystem of supporting libraries like matplotlib for plotting and visualization, OpenCV for image and video processing, and pandas for file I/O and data analysis. Instead of reinventing the wheel, PyTorch interoperates really well with NumPy to leverage its existing ecosystem of tools and libraries. Let's take a look at an example of a NumPy array. Again, NumPy is already installed since we've cloned the notebook with Jovian and installed all the dependencies using Conda. So the first step is to import NumPy as NP. Then this is a common convention that everybody follows. And to create an array, we simply say np.array and pass the data inside it. So in this case, I'm actually creating a matrix. We can convert a NumPy array to a PyTorch tensor using torch.fromNumPy. We can also simply pass the NumPy array into torch.tensor, but in this case, it creates a copy of the array. Right? So if you do not want to create a copy of the data, use torch.fromNumPy, otherwise use torch.tensor. And let's verify that the NumPy array and the torch tensor have similar data types. And we can convert a PyTorch tensor to a NumPy array using the .toNumPy method of a tensor. So here I'm calling, well actually it's just the .numpy method of a tensor. And the interoperability between PyTorch and NumPy is really important because most datasets you'll work with will likely be read and pre-processed as NumPy arrays. With this, we have completed some discussion of tensors and gradients. And as a final step, we can save and commit our work using the Jovian library. So first I import Jovian and then I call the command jovian.commit. And I'm requested here to enter an API key which I can get from jvn.io. So I'm already logged in here, but you might have to log in to generate an API key. So I click copy API key, which copies the key to the clipboard, paste it here and press enter. So this saves the notebook. This also captures the Python environment and it puts it online where I can see my notebook and share it with anybody. And now others can click on the clone button and clone my notebook, complete with the Python environment and libraries that they need. Jovian also includes a powerful commenting interface so you and others can discuss and comment on specific parts of your notebook. Tensors in PyTorch support a variety of operations, and what we've covered here is by no means exhaustive. You can learn more about tensors and tensor operations by visiting the PyTorch documentation. As you can see here, tensors support dozens and dozens of different operations. And you can take advantage of this interactive Jupyter environment to experiment with tensors and try different combinations of operations discussed here. Right? Here are some of the things to try out. What if one or more of x, w, or b were matrices instead of numbers in the above example? What would the result y and the gradients w.grad and b.grad look like in this case? What if y was a matrix created using torch.tensor, which each element of the matrix expressed as a combination of a numeric tensors x, w, and b? Right? What would the gradients look like in that case? And what if we had a chain of operations instead of just one? What if we had y equals xw plus b and then z equals ly plus m and so on? What would calling w.grad do? And if you're interested, you can learn more about matrix derivatives on Wikipedia, although it's not necessary to follow along, and we'll cover the material as and when it is relevant. With this, we complete our discussion of tensors and gradients in PyTorch, and we're ready to move on to the next topic, linear regression. Continuing where the previous tutorial left off, we'll discuss one of the foundational algorithms of machine learning in this lesson, linear regression. We'll create a model that predicts crop yields for apples and oranges, and these are called the target variables, by looking at the average temperature, rainfall, and humidity in a region. So these are called the input variables, temperature, rainfall, humidity, and the things that we're trying to predict, the yield for apples and oranges, are called the target variables. And here is the training data that we are working with. This might be data collected over the past year from a different bunch of reasons, showing the average temperature, rainfall, humidity, and the corresponding yields of apples and oranges. In linear regression models, each target variable is estimated to be a weighted sum of the input variables offset by some constant known as a bias. What this means is the yield of apples is assumed to be some number W11 times the temperature plus some number W12 times the rainfall plus some number W13 times the humidity plus a small term B1, which is known as bias, and similarly for oranges. Visually, it means that the yield of apples is a linear or planar function of temperature, rainfall, and humidity. Now, since we can only show 3 dimensions here, I'm only showing temperature and rainfall. And as you can see, the relation that we see is that as the temperature increases or as the rainfall increases, overall the yield of apples also increases. Now the learning part of linear regression is to figure out the set of weights W11, W12, W13, so on, and B1 and B2 by looking at the training data so that we can make accurate predictions for new data. That is, to predict the yields of apples and oranges in a new region or in the next year using the average temperature, rainfall, and humidity values. And this is done by adjusting the weights slightly many times to make better predictions using an optimization technique called gradient descent. Don't worry if that doesn't make sense yet because we'll get into that in a lot of detail. Now, as with the previous post, if you want to follow along and run the code as you read, you can clone this notebook, install the required dependencies, and start Jupyter by running these commands. So I already have the Jovian library installed, so I don't need to run this. I definitely need to run the clone command. So what I'll do is I will go up here and click on the clone button, which copies the command to my clipboard. Then I need to go to my terminal. So looks like I'm still in the previous tutorial directory. So I will just come out of that directory. And I also need to deactivate this Python virtual environment that I'm currently inside. So I will simply run conda deactivate. And on older versions of Anaconda, you might have to run source deactivate to deactivate the environment. Okay, now I'm going to paste the clone command. So once again, I'm just going to copy the command here, come back to my terminal, paste the command. And this downloads the notebook and the environment used, which contains all the Python libraries, right? So now I'm inside the directory 02 linear regression. It has the notebook and the environment. I'm going to run conda env update. What this does is this installs all the required dependencies from the environment.yml file and creates a virtual environment. Okay, so now that is done. Now I can activate this environment by running conda activate 02 linear regression. Next, I start the Jupyter notebook by running the Jupyter notebook command. And once I do that, I can open the notebook up within Jupyter and start executing. Once again, just to make sure that I can generate these outputs myself, I'm going to click on kernel, restart and clear output, as I'm going to run the cells one by one. Okay, and we begin by importing NumPy and PyTorch. Now the training data, which is this table here, can be represented using two matrices, inputs and targets, each with one row per observation and one column per variable. What that means is the inputs array contains three columns. It's a matrix and it contains three columns, one for temperature, rainfall and humidity, and then each of the data points from the training data becomes one row, right? So as you see here, this row shows up here, right? And similarly, the corresponding target values are also represented as a matrix with one column for the yield of apples and one column for the yield of oranges, right? And we've separated the input and target variables because we'll operate on them separately. Also, we've created NumPy arrays because typically this is how you would work with the training data. You might maybe read some CSV files or Excel files or a database dump as NumPy array, do some pre-processing, do some exploratory analysis, and then convert them into PyTorch tensors as follows. Right, so let me quickly run these. Okay, so now once I call torch.from NumPy on the inputs and targets, I get back the PyTorch tensors. Now the weights and biases can also be represented as matrices initialized as random values, right? So the first row of the weights matrix W and the first element of B are used to predict the first target variable, that is the yield of apples, and similarly the second of orange for oranges, right? So this is the weights matrix. It has two rows. This row corresponds to W11, W12 and W13, and similarly the second row for this. And similarly the bias is a vector which has two values, this for apples and this one for oranges, right? And we have used torch.randn here, which creates a tensor with the given shape with the elements picked randomly from a normal distribution with the mean 0 and standard deviation 1. Don't worry if you don't understand what that means. You can learn more about it here. But for all practical purposes, what this means is it gives us a bunch of random numbers which are close to in the range of 0 to 1 or 0 to -1. Okay. Now our model is simply a function that performs a matrix multiplication of the inputs and the weights, and the weights are transposed so that the dimensions line up. And it also adds the bias which is replicated for each observation, right? So as you can see here, here I have the inputs matrix, here I have the weights matrix, it's transposed. So once you multiply that, this row gets multiplied with this column. So I get 73 times W11, 67 times W12 and 43 times W13 plus B1. That becomes the first column of the output, and similarly the same numbers multiplied with this column, that becomes the second column of the output, right? So let's see that in action. And we can define the model very simply as a function. So it takes some input and it returns x, and here I'm using the @ character for matrix multiplication multiplied, so x multiplied by W transpose plus B. Okay. And the matrix obtained by passing the input data into the model is a set of predictions for the target variables. So let us try and generate the predictions. So I pass the model, I pass the inputs into the model, which performs this calculation, and then I print out the output, right? So this is the output that I get. For each input observation, I get two outputs. And the first one is supposed to represent the predicted yield of apples, and the second represents the predicted yield of oranges. So let us compare the predictions of our model with the actual target variables, right? So as you can see, there is a huge difference between the predictions of our model and the actual values of the target variables. In fact, in this case, a lot of these don't even make sense. For instance, the yield of oranges cannot even be negative, right? But obviously this is because we've initialized our model with random weights and biases, and we can't expect it to just work, right? And so before we improve our model, we need a way to evaluate how well our model is performing. We can compare the model's predictions with the actual targets using the following method. First, we calculate the difference between the two matrices, predictions and targets. Then we square the elements of the difference matrix to remove any negative values. And finally, we calculate the average of all the elements in the resulting matrix, right? So this results in a single number, which is known as the mean squared error, or MSE. So let's define that as a function first. And this is always a good idea to always define functions for any operations that you're performing, so that you can repeat them with different inputs very easily, right? So MSE takes two arguments, T1 and T2. First, it calculates the difference between the arguments. Then it performs a diff star diff, and then the star here performs an element wise multiplication. So this is not a matrix multiplication, but it simply multiplies the corresponding elements together, and which essentially in this case squares each element of the difference matrix. Then calling torch.sum adds up all those squared elements, and finally calling diff.numel returns the number of elements in the diff matrix. So this gives us the average of all the elements in the resulting squared summed matrix, right? So let us compute the mean squared error for the current predictions of our model, right? So we print this out, and this looks like it's a pretty large number, and this is how we can interpret the results. Now, on average, each element in the prediction differs from the actual target by the square root of 15224. So that's about 123, right? So our each element in our target is off by about 123, which is quite bad, because the numbers that we're predicting are themselves in just the range of maybe 50 to 100 or 50 to 120 or so on, right? And also this result is called a loss because it indicates how bad the model is at predicting the target variable. So lower the loss, the better the model, right? And with PyTorch, as we've seen before, we can automatically compute the gradient or the derivative of the loss with respect to the weights and biases because they have requires grad set to true, right? So if we go back here all this way, you can see that we have set requires grad to true for the weights and the biases. And so let us see how we can compute these gradients. So when I call loss dot backward, the gradients are computed and stored in the dot grad property of the respective tensors. Now note that the derivative of the loss with respect to the weight matrix is itself a matrix, and it has the same dimensions as the weights matrix, right? So once I let me just print this out. So as you can see here, you have this is the weights matrix, and this is the corresponding gradient matrix, right? So loss is a number, but W is a matrix. So what this particular number represents, this particular element of the gradient represents the derivative of the loss with respect to this corresponding element of the weight matrix. And similarly, the second element represents the gradient with respect to this element, and so on, right? Now, since the loss is a quadratic function of our weights and biases, and our objective is to find the set of weights where the loss is the lowest. Now, if we plot a graph of the loss with respect to any individual weight, for instance, with respect to this particular element of the weight, keeping all the other elements constant, it will look like this kind of a figure. Okay, and a key insight from calculus is that the gradient indicates the rate of change of loss, or the slope of the loss function with respect to the weights and the biases, right? So if we if this is how the loss changes as a particular element of the weight is modified, as increased or decreased, keeping other things constant, then the gradient which is this element represents the slope of this line. if the gradient is positive, which means it means the slope is increasing. If the gradient is negative, it means the slope is decreasing, right? So if the gradient element is positive, increasing that particular weight slightly will increase the loss, as it happens in this case, and decreasing the element's value slightly will decrease the loss. Okay. Similarly, if a gradient element is negative, then increasing the element's value slightly will decrease the loss because the slope is in a decreasing direction, and decreasing the element's value slightly will increase the loss. Right. So and also the increase or decrease in loss by changing a weight element is proportional to the value of the gradient of that loss with respect to that element, right? So if the gradient is larger, then the increase or decrease is larger, but if the gradient is smaller, then the increase or decrease is smaller. And this forms the basis for the optimization algorithm that we'll use to improve our model. It is called gradient descent. But before we proceed, we have one final step to take care of. So that is to reset the gradients back to zero by calling the dot zero method, right? So we need to do this because PyTorch accumulates gradients. That is, the next time we call dot backward on the loss, the new gradient values will get added to the existing gradient values, right? So w.grad will first get the first set of gradient values, and then if we recompute the loss and call loss.backward once again, w.grad will retain those original value of the gradient, but it will also add on the values of the new gradients, and this can lead to problems sometimes because we want fresh gradients each time. So by calling w.grad.zero underscore, we set these gradients back to zero. Okay. So now we're ready to actually improve our model by adjusting the weights and biases using the gradient descent optimization algorithm. And this will help us reduce the loss. Now this algorithm has the following steps. The step one is to generate the predictions. So let's just run that. We are passing the inputs into the model and getting the predictions. Then step two is to calculate the loss. Right, and the predictions and the loss are both the same as before since we haven't made any changes to our model. Okay, then step three is to compute the gradients with respect to the weights and the biases. So let us call loss.backward. This will compute the gradients. And finally, the step 4 is to adjust the gradients by subtracting a small quantity proportional to the gradient. Right, so adjust the weights and the biases actually, not the gradients, right? And this is the insight that we learned here, that if a particular that if we move in the direction opposite to the gradient, that is, if the gradient is positive, we decrease that particular element, and that will decrease the loss. And if the gradient is negative, we increase that element, and that will decrease the loss. Right. So by subtracting a small quantity proportional to the gradient, we can reduce the loss, right? And this will modify the weights slightly. Now, why are we doing a small quantity proportional to the gradient? Because if you notice here, the gradients can often have very large values, right? And we don't want these large values to completely throw off our weights. We want to take a small step in this direction, but we don't want to suddenly jump to this point, okay? Because that is bad. That's going to increase the loss. So that's what we're doing here. First, we call torch.nograd. So torch.nograd indicates to PyTorch that we shouldn't track, calculate, or modify gradients while updating the weights and biases, since we are already done with the gradient computation and we want to use them to change the weights themselves. Okay, then inside we call w minus equals w.grad multiplied by 10 to the power minus 5. Okay, so this subtracts a small quantity proportional to the gradient from each element of the weight. Similarly, it subtracts a small quantity proportional to the bias from each element of the bias. Okay, and finally we call w.grad.0 and b.grad.0 to reset the gradients back to 0. Okay, so now once we run this, we have slightly changed the weights and biases, right? And we have done this by taking a small step in the downhill direction of the gradient. Okay, and the small number that we have used to restrict how large a step we are taking is called the learning rate of the algorithm. Now, after we have updated the weights, we reset the gradients back to 0, and this is to avoid affecting any future computations. Okay, so now let's look at the new weights and biases. As you can see here, the weight has been changed slightly. If you look at this particular element, currently it is minus 0.7791, and earlier it had the value minus 0.8332, right? And you can see a similar change for all of these values. With the new weights and biases, the model should now have a lower loss. Okay, so now the model's loss is this, which is about 10,501, and in the previous case the model's loss was about 15,000. So we have already achieved a significant reduction in the loss simply by adjusting the weights and biases slightly using the gradient descent algorithm. Now, to reduce the loss further, we can repeat the process of adjusting the weights and biases using the gradients multiple times. Each iteration is called an epoch. So let's train the model for 100 epochs. So again, for I in the range 100, we first calculate the predictions, then we generate the loss, then we calculate the gradients by calling loss.backward. Then, without affecting the gradients, by setting torch.nograd, we subtract a small quantity proportional to the gradients from the weights and the bias. And finally, we set the weights and bias gradients back to 0. Okay, now once again, let's verify that this loss is now lower. That's great. So our loss has come down by from 10,501 to about 337. Right now, as you can see, the loss is now much lower than what we started out with. And let's look at the model's prediction and compare them with the targets. So these are the predictions of the model, and these are the targets. Clearly, our model is now doing a really good job. The predictions are now quite close to the target variables, and we can get even better results by training for a few more epochs. Continuing where we left off, we are now going to re-implement linear regression using some built-ins in PyTorch. The model and training process that we used were implemented using basic matrix operations, but since this is such a common pattern, PyTorch has several built-in functions and classes to make it easy to create and train models. So let's begin by importing the torch.nn package from PyTorch, which contains utility classes for building neural networks. As before, we represent the inputs and targets as matrices. And then we convert them into PyTorch tensors. In this case, we are using 15 training examples instead of 5 to illustrate how to work with large datasets in small batches. And this is quite useful when you have data with hundreds of thousands or even millions of rows, and you cannot fit the entire dataset into memory. So what we do is we pick a small batch of data of maybe a few hundred rows or so, and then we pass that into our gradient descent algorithm to improve the model step by step. And then we repeat with all the batches in the data. So we'll create a tensor dataset which allows access to the rows from inputs and targets as pairs or tuples, and provides standard APIs for working with many different types of datasets in PyTorch. So first I import tensor dataset, and all I have to do in this case is to pass in the inputs and targets to tensor dataset. Let's create a training dataset this way, and then look at the first 3 elements of this dataset. So as you can see, this returns a pair, which is a couple of elements, the first among which is the first 3 rows from the training data inputs, and the second element of the pair is the first 3 outputs, right? So the tensor dataset allows us to access a small section of the training data using the array indexing notation. It returns a pair in which the first element contains the input variables and the second element contains the targets. We'll also create a data loader which can split this data into batches of a predefined size while training. It also provides other utilities like shuffling and random sampling of the data. Shuffling can be quite useful as it can lead to faster convergence in the gradient descent algorithm. So this is what we are doing. We are importing the data loader here, and then we are setting the batch size to 5. And then inside the data loader, we simply need to pass the training dataset, the batch size, and we're also setting shuffle equals to true. Now the data loader is typically used in a for in loop. So let's look at an example. So here I'm saying for xb and yb, which represents the first batch of inputs and targets in training data loader. I will print them out and then I will break the loop. Right? So this is the first batch of data and this is the second batch of data. As you can see, it has been picked random. It has been picked from a shuffled training data set. Now in each iteration, the data loader returns one batch of data with the given batch size, and it shuffles the training data before creating batches. Shuffling helps to randomize the input to the optimization algorithm, and it leads to a faster reduction in the loss. Now, instead of initializing the weights and biases manually, we can define the model using the nn.linear class from PyTorch, which does all of these things automatically. Right? So now instead of defining a function, we can simply say model is nn.linear. We pass in the number of input variables, which is 3, and the number of output variables, which is 2. And inside the model contains a weight and bias, which have a similar shape as the weight and bias that we had defined manually. PyTorch models also have a helpful dot parameters method, which returns a list containing all the weights and bias matrices present in the model. So for our linear regression model, we have one weight matrix and one bias matrix. And we can use this model to generate predictions in the exact same way as before, which is by passing the inputs. And once again, the predictions of our model are fairly bad and are nowhere close to our targets because we have started with a random set of weights and biases. Now, instead of defining a loss function manually, we can use the built-in loss, MSE loss. This is present inside the torch.nn.functional package, which is often imported as F. The nn.functional package contains many useful loss functions and several other utilities. So in this case, we are simply going to use the MSE loss, and let's compute the loss for the current predictions of our model. So we generate the predictions by passing the inputs into the model, and then we pass the model predictions and the targets into the loss function. Now, instead of manually manipulating the model's weights and biases using gradients, we can use the optimizer optim.sgd, which PyTorch provides. SGD stands for stochastic gradient descent. It is called stochastic because the samples are selected in batches and often with random shuffling, as in this case, instead of as a single group. So let us define this optimizer. We instantiate the torch.optim.sgd class, and it requires the model parameters to be passed in as well as the learning rate. Right? This learning rate is the same small quantity by which we will multiply the gradients before subtracting them from that corresponding weights and biases. Now note that model.parameters is passed as an argument to optim.std so that the optimizer knows which matrices should be modified during the update step. We are now ready to train the model, and we'll follow the exact same process to implement gradient descent, which is we generate the predictions, calculate the loss, compute gradients with respect to the weights and biases. Then we adjust the weights by subtracting a small quantity proportional to the gradient, and this will be done by the optimizer. We don't have to do it manually. And finally, we reset the gradients back to 0. The only change is that we'll work with batches of data instead of processing the entire training data in every iteration, right? So let's define a utility function fit, which trains the model for a given number of epochs. So the fit function takes the number of epochs, the model, the loss function, and the optimizer. And for the given number of epochs, it picks out batches out of the training data loader, right? And then it generates the predictions, it calculates the loss, it computes the gradients of the loss with respect to the weights and biases. And now instead of manually updating the weights and biases, it simply calls opt, which is the optimizer dot step. And now the weights have been modified, and then it resets the gradients back to 0, and this again can be done using opt.0grad. Okay, and also at the end of each epoch, once all the batches have been processed, we will also print the progress of the algorithm for every 10th epoch, right? So we are simply printing out the epoch number and the loss. And remember, this is the loss coming from the last batch of the training data for that particular epoch. Okay, so a few things that we need to note about is that the data loader is defined. We're using data loader to get the batches of data, and then we are making the changes directly using which is the optimizer, right? And the loss dot item that you see here, this simply picks out the single number which is present inside the loss tensor. Okay, so now let's train the model for 100 epochs, and it's done already. As you can see, the loss reduces overall, and it comes down to a really small value, right? And now we can generate the predictions of our model and verify that we're actually quite close to our targets. So these are the predictions. We get the predictions by passing the inputs into the model, and these are the targets. And clearly, the predictions are quite close to the targets. And so now we have a fairly good model to predict crop yields for apples and oranges by looking at the average temperature, rainfall, and humidity in a region. Okay, and as a final step, we can save, commit, and upload the notebook using the Jovian library. So we import Jovian, and then we call jovian.commit. And once again, this requires me to enter an API key. So I can go to jovian.io. I can log in if I need to. Then I can copy the API key and paste it here. So this saves the notebook, it uploads the notebook, it captures the Python environment and I need to run my notebook, and then it puts it online on this web page, which you can share with anyone else. And others can now reproduce your work by clicking the clone command. Okay. So we've covered a lot of ground in this tutorial, including linear regression and gradient descent. So and here are a few more resources if you'd like to dig deeper into these topics. So for a more detailed explanation of derivatives and gradients, you can see these notes from a Udacity course. And for an animated visualization of linear regression, you can check out this blog post. And then just to quickly walk through it, this is the data that we're trying to model using a linear regression model. In this case, there's just one input and one output. The way we start out is we start out by a random line that we that we create, and then we try to slightly change the slope and the intercept of the line, which in this case are corresponding to the weights and biases, so that it keeps getting better and better, right? And here is an animation which shows you how the line actually fits. Okay, I do recommend that you try this out as well. And for a more mathematical treatment of matrix calculus, linear regression, and gradient descent, especially if you have some background in these topics, you should check out Andrew Ng's excellent course notes from the Stanford University CS229 course. I have added the link here. And to practice and test your skills, you can participate in the Boston House Prize Prediction Competition on Kaggle. So Kaggle is a website that hosts data science competitions, and what you can do is you can download the dataset. In this case, the dataset contains some information like the prices of houses in based on a bunch of other parameters. Right, and then you have to create a model to create predictions on an unknown set of houses where you have the parameters but you don't have the prices, and this will help you practice your skills. Okay, so with this we complete our discussion of linear regression in PyTorch, and we are ready to move on to the next topic, a logistic regression. In this tutorial, we'll use our existing knowledge of PyTorch and linear regression to solve a very different kind of problem: image classification. We will use the famous MNIST handwritten digits database as our training dataset. It consists of 28 pixel by 28 pixel grayscale images of handwritten digits from 0 to 9, along with labels for each image indicating which digit it represents. So here are some sample images from the dataset. If you want to follow along and run the code as you read, you can clone this notebook and install the required dependencies using Conda. So let's do that. I have copied the clone command. So I don't need to install the library since I already have it installed. I'm going to run the clone command on my terminal. Next, I can go inside the directory and run conda env update to install all the required dependencies. Now I can activate the virtual environment using conda activate. And finally, I can start the Jupyter notebook by running Jupyter notebook. I open up the notebook 03logisticregression.ipynb. Now that I have the notebook open, we begin by importing Torch and Torch Vision. So Torch Vision contains some utilities for working with image data. It also contains helper classes to automatically download and import popular datasets like MNIST. I'm going to go ahead and clear all the outputs so that I can run the cells myself. To download the training set, I create an instance of the MNIST class inside torchvision.datasets. Now when this statement is executed for the first time, it downloads the data to the data directory next to the notebook and creates a PyTorch dataset. On subsequent executions, the download is skipped as the data is already downloaded. Now let's check the size of the dataset. So the dataset has 60,000 images which can be used to train the model. And there is also an additional dataset of 10,000 images used for testing, which can be created by passing train equals false to the MNIST class. Now let's look at a sample element from the training dataset. So it's a pair consisting of a 28 by 28 image and a label. The image is an object of the pil.image.image class, which is a part of the Python imaging library below. We can view the image within Jupyter using matplotlib, which is the de facto plotting and graphing library for data science in Python. So we import matplotlib.pyplot as plt, and then we add this special command matplotlib inline. The special statement matplotlib inline is added to indicate to Jupyter that we want to plot the graphs within the notebook. Without this line, Jupyter will show the image in a pop-up, and the statement starting with the percentage sign are called IPython magic commands and are used to configure the behavior of Jupyter itself. So let's look at a couple of images from the dataset. First, as we get the first element of the dataset, it returns a pair of an image and a label. Then we pass the image to plt.imshow, which displays the image. And finally, we also print out the label for reference. So here is the image. It is a 28 pixel by 28 pixel image, and the label is 5. Let's take a look at another image. So it's evident that these images are quite small in size, and recognizing the digits can sometimes be hard even for the human eye. And while it's useful to look at these images, there's just one problem here. PyTorch doesn't know how to work with images. So we need to convert the images into tensors. And we can do this by specifying a transform while creating our dataset. So PyTorch datasets allow us to specify one or more transformation functions which are applied to the images as they are loaded. So torchvision.transforms contains many such predefined functions, and we'll use the toTensor transform to convert images into PyTorch tensors. Now let us take a look at a sample element from the dataset once again. So the image is now converted into a 1 by 28 by 28 tensor. And the first dimension is used to keep track of the color channels. Since images in the MNIST dataset are grayscale, there is just one channel here. Other datasets have images in color, in which case there are three channels: red, green, and blue. So let's look at some sample values inside the tensor. So I'm picking out the 10th to 15th row and 10th to 15th column of the image tensor. And I'm also printing out the maximum value inside the image tensor and the minimum value. So this will help us understand the range of values. So the values range from 0 to 1, with 0 representing black and 1 representing white, and the values in between the different shades of gray. We can also plot the tensor as an image using the plt.imshow method. Note that this region printed here corresponds to this area of the image. And also that we need to pass the 28 by 28 matrix to the plt.imshow without the channel dimension. And we can also pass a color map, cmap equals gray, to indicate to PyTorch, to indicate to PyPlot that we want to see a grayscale image. While building real-world machine learning models, it is quite common to split the dataset into three parts: the training set, and used to train the model, that is, compute the loss and adjust the weights of the model using gradient descent; the validation set, which is used to evaluate the model while training, adjust hyperparameters like learning rate, etc., and pick the best version of the model; and the test set. This is used to compare different models or different types of modeling approaches and report the final accuracy of the model. In the MNIST dataset, there are 60,000 training images and 10,000 test images. The test set is standardized so that different researchers can report the results of their models against the same set of images. Now, since there's no predefined validation set, we must manually split the 60,000 images into training and validation datasets. So now let's define a function that randomly picks a given fraction of the images for the validation set. So we import numpy as np, and then we define a function split indices, which takes in a number n, which is the size of the dataset, and a percentage which we want to set aside for the validation set. So first we calculate the size of the validation set, then we create a random permutation of 0 to n minus 1. So this gives us a random permutation of all the indices in the training set. And then we pick the first n val indices for the validation set. So this is where we do that, and the remaining indices are used as the training data set. So note that it's important to shuffle the indices before creating a validation set, because the training images are often ordered by the target labels. That is, you might have images of zeros followed by images of ones followed by images of twos and so on. So if we were to pick a 20% validation set simply by selecting the last 20% of the images, now the validation set would only consist of images of 8s and 9s, whereas the training set would contain no images of 8s and 9s. So this would make it impossible to train a good model using the training set, which also performs well on the validation set and on real world data. Okay, so now let us use the split indices function to create a set of training and validation indices. Okay, so now let's see how many we have created here. So we have 48,000 indices in the training set and 12,000 indices in the validation set. And these are some sample indices from the validation set, and as you can see, they are picked completely at random. So we have set aside a small portion of 20% to set as the validation set, and we can now create a PyTorch data loader for each of these using a subset random sampler, which samples elements randomly from a given list of indices while generating the batches of data. So we import subset random sampler and we import data loader. The first sampler that we create is for the training set, to which we pass in the training indices, and then we create the training data loader by passing in the data set, the batch size, which is 100 in this case, and the training sampler. Now the validation loader is almost identical, except that it uses a validation sampler which is created using the validation indices. Okay, so now that we have prepared our data loaders, we can define our model. A logistic regression model is almost identical to a linear regression model. That is, there are weights and bias matrices, and the output is obtained using a simple matrix operation. That is, the prediction is equal to the input multiplied, so there's a matrix multiplication multiplied by the transpose of the weights with the bias added. So if you've seen the linear regression tutorial, this should be pretty obvious. And just as we did with linear regression, we can use nn.linear to create the model instead of defining and initializing the matrices manually. Now, since the nn.linear expects each training example to be a vector, each of the 1 by 28 by 28 image tensors need to be flattened out into a vector of size 784, which is 28 by 28, before being passed into the model. And finally, the output of the model of the model for each image is a vector of size 10, with each element of the vector signifying the probability of a particular target label, that is the labels 0 to 9. And the predicted label for an image is simply the one with the highest probability. Okay, so let's see how we implement this. So first we import torch.nn as nn. Then this is the input size, which is 28 by 28, and the output size, which is equal to the number of classes, that is 10 in this case, right? And then the model is simply nn.linear with the input size and the number of classes passed into it. Now, of course, this model is a lot larger than our previous model in terms of the number of parameters, right? So let us take a look at the weights and biases. So model.weight is a 10 by 784 matrix, and model.bias is a vector of size 10, right? So although there are a total of 7,850 parameters here, conceptually nothing has changed so far. So let's try and generate some outputs using our model. We'll take the first batch of 100 images from our dataset and pass them into the model. So this is what we're doing here. So we do a for loop with the train loader, and we get back batches of data, which is images and labels. We're also printing out the shape of images just to see what it looks like. And then we pass the images into the model to get the outputs. And finally we break out because we just want to look at the first batch of data. So as you can see, the images are of the shape 100 by 1 by 28 by 28. This is a single image and this is the size of the batch. Now we get an error here which says that there is a size mismatch. The expected size is 784 by 28 by 10, and this seems to be a completely different size here, right? So the error is because the input data does not have the right shape. Our images are of the shape 1 by 28 by 28, but we need them to be vectors of the size 784. So we need to flatten them out. So we'll use the dot reshape method of a tensor, which allows us to effectively view each image as a flat vector without really changing the underlying data. And to include this additional functionality within our model, we need to define a custom model by extending the nn.module class from PyTorch. So we define a class called mnist model, which extends nn.module, and this is a constructor init, and inside the init constructor method we call super. This is just some syntax that we have to follow in Python, so that we have to call the init method of the super class, and then we instantiate the weights and biases using nn.linear, and we set it inside the .linear attribute of this model. Okay, then we also need to define a forward method. So this is the method that is invoked when we pass a batch of inputs into the model. So in the forward method, we get a batch of data as an input, and we call xb, which is a batch of data, dot reshape -1, 784. Right, so xb.reshape -1, 784 indicates to PyTorch that we want a view of the xb tensor with 2 dimensions, where the length along the second dimension is 28 by 28 or 784. Right, and one of the arguments to reshape can be set to -1. In this case, we are setting the first dimension, and to let PyTorch figure it out automatically based on the shape of the original tensor. So since the original tensor is of the shape 100 by 1 by 28 by 28, now these three become combined into 784. So the first dimension is of length 100. Now the advantage with putting -1 here is that we can work with batches of different sizes and we don't have to hard code a particular batch size inside our model. Okay, so now that once we have reshaped the input batch, we can then pass it into self.linear and get the outputs of the model, and we return the output. So with this, the definition of our custom model class is complete, and we can instantiate it into a variable called model. Note that the model no longer has a .weight and .bias attribute, as they are now inside the .linear attribute. But it does have a .parameters method which contains a list of weights and biases and can be used with a PyTorch optimizer. And our new custom model can be used in the exact same way as before. So let's see if it works. So there you go. As we pick a batch of data from the train loader and we pass it into the model, we get back an output of the size 100 by 10. So we have a vector of size 10 for each image that was passed in. And this is one of the sample outputs, and this is another. So for each of the 100 images, we get 10 outputs, one for each class. And as discussed earlier, we'd like these outputs to represent the probabilities for these particular classes 0 to 9. But for that, the elements of each output row must lie between 0 to 1, and they must add up to 1, which is clearly not the case here, as we have a bunch of negative values and some values can be larger and some are smaller. So to convert the output rows into probabilities, we use the softmax function, which has the following formula. So first we replace each element yi in the output row by e to the power yi, which makes all the elements positive. Then we divide each element by the sum of all the elements to ensure that they add up to 1. Now while it's easy to implement the softmax function, and you should try it, we will use the implementation that is provided within PyTorch because it works well with multi-dimensional tensors, which in this case is a list of output rows. So we import torch.nn.functional as f, which is where the softmax function is included, and we invoke the softmax function on the outputs while also providing the dimension along which the softmax must be applied. Notice that we must apply the softmax independently for each output row. That is why we pass dimension equal to 1. So let us do that and let us look at some sample probabilities. So this is the output of this is the probabilities based on this row, right? So each of these have been first raised to the power of e. Each of these have been raised to e to the power yi, and then they have been divided by the total, converting them into probabilities, right? So as you can see now, each row now sums up to 1. And finally, we can determine the predicted label for each image by simply choosing the index of the element with the highest probability in each row. And this is done by using torch.max, which returns the largest element and the index of the largest element along a particular dimension, right? So we call torch.max on the probabilities along the first dimension. This returns the value of the maximum probability and the predictions. And we can print out these predictions. As you can see, these are the predicted labels for the 100 images that we passed in. And the numbers printed above, let's compare them with the actual labels. Okay, so if you look carefully, clearly the predicted and the actual labels are completely different. And obviously that's because we have started with the randomly initialized weights and biases. So we need to train the model, that is adjust the weights and biases using gradient descent to make better predictions. Just as with linear regression, we need a way to evaluate how well our model is performing. And a natural way to do this would be to find the percentage of labels that were predicted correctly. Right? So if these are the predictions and these are the labels, all we need to do is find out how many labels match the predictions. And this is called the accuracy of the predictions. So let's define a function called accuracy, which takes in the two lists. And first we call the equals operator, which performs an element-wise comparison of the two tensors with the same shape and returns a tensor of the same shape containing zeros for unequal elements and ones for the equal elements. Then passing this result to torch.sum returns the number of labels that were predicted correctly, right? Finally, we get the value out of it by calling .item, and then we divide by the length of the list to get the average value, which is the accuracy. So let's calculate the accuracy of the current model on the first batch of data. Obviously, we expect it to be pretty bad. So it's about 8%, right? And while the accuracy is a great way for us humans to evaluate the model, it can't be used as a loss function for our model using gradient descent for a bunch of reasons. The first is that it is not a differentiable function, right? So torch.max and equals both are non-continuous and non-differentiable operations. So we can't use the accuracy for computing gradients with respect to the weights and biases. Second, it doesn't take into account the actual probabilities predicted by the model. So it can't provide sufficient feedback for incremental improvements. So due to these reasons, accuracy is a great evaluation metric for classification, but not a good loss function. A commonly used loss function for classification problems is the cross entropy, which has this following formula. So the cross entropy for a single output takes in the list of probabilities and the output label represented as a vector with the index of the output label set to 1, and it simply sums them up by applying a logarithm to the probability and multiplying it with the corresponding output label value. And finally, there's a negative sign, right? So while it looks complicated, it's actually quite simple. So for each output row, we pick out the predicted probability of the correct label. That is, if the predicted probabilities for an image are 0.1, 0.3, 0.2, etc., and the correct label is 1, which is the second index, we pick out the corresponding element 0.3 and ignore the rest. Then we take the logarithm of the picked probability, and if the probability is high or close to 1, then its logarithm is a very small negative value close to 0. And if the probability is low, which is close to 0, then its logarithm is a very large negative value, right? So we also multiply the result by -1, which results in a large positive value of the loss for poor predictions. And finally, we take the average of the cross entropy across all the output rows to get the overall loss for a batch of data. So unlike accuracy, the cross entropy is a continuous and differentiable function that also provides good feedback for incremental improvements in the model. That is, a slightly higher probability for the correct label leads to a slightly lower loss, right? And this makes it a good choice for the loss function. And as you might expect, PyTorch provides an efficient and tensor-friendly implementation of cross entropy as part of torch.nn.functional. Moreover, it also performs softmax internally, so we can directly pass the outputs of the model without converting them into probabilities. So let's run this. And let's calculate the loss for the current batch of data. So we pass in the output probabilities and we pass in the labels to the loss function. So the loss is around 2.3, and since the cross entropy is the negative logarithm of the predicted probability of the correct label averaged over all the training samples, one way to interpret this number, the result 2.3, is to look at e to the power -2.3, which is around 0.1, as the predicted probability of the correct label on average, right? So lower the loss, higher the predicted probability, and better the model. So we are going to use the optim.sgd optimizer to optimize the weights and biases during training. But this time we are going to use a higher learning rate of 10 to the power -3. So let's define the optimizer. Note that we need to pass in the model.parameters to the optimizer. And parameters like batch size, learning rate, etc. need to be picked in advance while training the machine learning model, and these are called hyperparameters. Picking the right hyperparameters is critical for training an accurate model within a reasonable amount of time, and it is an active area of research and experimentation. So feel free to try different learning rates and see how it affects the training process. Now that we have defined the data loaders, model, loss function, and optimizer, we are ready to train the model. The training process is almost identical to linear regression. However, we will augment the fit function we defined earlier to evaluate the model's accuracy and loss using the validation set at the end of every epoch. So we begin by defining a function loss batch, which calculates the loss for a batch of data. That's what we are doing here. Optionally, it performs the gradient descent update step if an optimizer is provided, right? So if the optimizer is not none, we compute the gradients, we update the parameters, and then we reset the gradients back to 0. Optionally, it also computes a metric, for example, accuracy, using the predictions and the actual targets, right? So we are making it generic so we don't hard code the accuracy metric into the function, right? So if we pass in a metric function, and if the metric is not none, then we compute the result of that particular metric by passing the predictions and the actual labels, right? And finally, we return the loss, we return the length of the batch, and we return the metric. The length of the batch is also returned as a part of the result because it will be useful while combining the losses and metrics for the entire dataset, right? So what can happen is that if you have let's say you have a data of size 90 and your batch size is 20, then your last batch is going to be slightly smaller. So if you want to combine the loss and the metric result for all the batches, you're going to need to take into account the size of each batch. Next, we define an evaluate function which calculates the overall loss and a metric if it is provided for the validation set, right? So the evaluate function takes in the model, the loss function, a validation data loader, and a metric, right? And with torch.nograd, since we are not doing this for gradient descent and we don't need to keep track of the gradients or derivatives, we pass each batch through the model. So I'm using a list comprehension here. We get batches of data from the validation data loader, and then we pass them into loss batch. Then, since we get a 3 tuple for each of these results, we can then separate them out into different lists using the zip function. So we get back a list of all the losses, a list of all the batch sizes, and a list of all the metric values. Okay. So the total size of the dataset is simply the sum of all the batch sizes. Then to get the average loss across batches, we multiply the losses with the corresponding batch sizes. We sum up to get the total loss and divide by the total number of elements in the dataset. Similarly, if the metric is available, we calculate an average value of the metric by first multiplying each of the metrics by the particular batch sizes, getting the total and dividing by the total size of the dataset. And finally, we return the average loss, the total size of the dataset, and the average metric. And if it's not immediately clear what this function does, try executing each statement in a separate cell and just look at the results. Next, we also need to redefine the accuracy function we had defined earlier to operate on an entire batch of outputs directly, so that we can use it as a metric in fit. So we take the model outputs and we take the labels, and we use torch.max to simply pick out the index of the output with the maximum value in each row. This gives us the predictions of the model, right? And then we use torch.sum and pass into it preds equal to labels, which returns a tensor of zeros and ones, and torch.sum then adds them up to give us the total number of correctly predicted labels, and divide them by the length of the predictions, which is the number of elements, to get back the accuracy of the batch. Right, so note that we don't need to apply softmax to the outputs, since softmax doesn't change the relative order of the results, right? So this is because e par x is an increasing function. That means if y1 is greater than y2, then e to the power y1 is greater than y2, and then the same holds true after averaging out the values to get the softmax. Okay, so let's see how the model performs on the validation set with the initial set of weights and biases. So I pass in to evaluate the model, the loss function, the validation data loader, and the metric accuracy. This gives me the validation loss. This is the loss averaged over the entire data set. Then it gives me the total length of the validation set, and it gives me the accuracy of the validation set. So once I run this, I need to run this first. So Yeah, so now we get back an accuracy of about 10%, and which is what one might expect from a randomly initialized model, since it has a 1 in 10 chance of getting a label right by guessing randomly, right? And also note that we are using the dot format method of the message string here to print only the first 4 digits of after the decimal point. This simply makes it a little easier to look at the result, right? So we can now define the fit function, which actually performs the gradient descent for a given number of epochs, and we can use the loss batch and evaluate functions internally, right? So the fit function takes the number of epochs, it takes the model, it takes the loss function, the optimizer, the training and validation data loaders, and optionally a metric, right? So for it goes into the number of epochs, and then for each in each epoch we first we train the model. This is simply by getting batches of data from the training data loader and passing them into loss batch. Then we evaluate the model. So we pass in this case we call evaluate, and we pass in the validation data loader. Note that the evaluation is done at the end of every epoch, right? Then we print the progress. So if we have a metric, then we print out the epoch number, the loss, and the metric. Otherwise we simply print out the epoch and the loss, right? And note that you can get the name of the metric function by calling metric dot underscore underscore name. So let us run this. Let's train the model for 5 epochs and take a look at the results. But before I do that, I'm going to redefine the model and the optimizer. This is handy to have it here, so that in case I need to reset the model, or I need to I encounter some kind of error, I can quickly reinstantiate the model without having to go up all the way. Okay, so now we call the fit function and we pass in all the right parameters. And as you can see, the model training takes a lot longer in this case because we have 60,000 images, each of size 28 by 28, and the matrices, the weight and bias matrices are also quite large. So now as the model is training, we get back a loss, the loss continues to decrease over time, and the accuracy of the model increases with time. And so that's a great result. With just 5 epochs of training, our model has reached an accuracy of over 80% on the validation set, right? So let's see if we can improve that by training for a few more epochs. So while the accuracy does continue to increase as we train for more epochs, the improvements get smaller with every epoch, right? And I have simply run this for 5 plus 5, 10 epochs here, but you can try running this for a couple more epochs and note down how the accuracy increases. And the increase will actually be easier to see using a line graph. So I have listed out the accuracies here from a previous run. I start with the initial accuracy, which is around 10%, and then I track the accuracy after every epoch. And then I'm using plt.plot to plot the accuracies. I will plot them as a line graph, and I will also mark out the actual points. I'm just going to set some labels here, epoch and accuracy, and finally set a title for the graph. So let me run this. So now you're looking at the accuracy versus number of epochs graph. It's quite clear that from the above picture that the model probably won't cross the accuracy threshold of 90% even after training for a very long time. So one possible reason for this is that the learning rate might be too high. It's possible that the model's parameters are bouncing around the optimal set of weights and biases that have the lowest loss. And you can try reducing the learning rate and training for a few more epochs to see if it helps. But the more likely reason is that the model just isn't powerful enough. If you remember our initial hypothesis, we have assumed that the output, which in this case is the class probabilities, is a linear function of the input, which in this case is the pixel intensities, right? And it is obtained by performing a matrix multiplication of the inputs with the weights matrix and adding the bias. Now, this is a fairly weak assumption as there may not actually exist a strictly linear relationship between the pixel intensities in an image and the digit it represents. And while it works reasonably well for a simple dataset like MNIST, and it gets us to 85% accuracy, which is not bad, we need more sophisticated models that can capture non-linear relationships between image pixels and labels for more complex tasks like recognizing everyday objects, animals, and so on. So while we have been tracking the overall accuracy of the model so far, it's also a good idea to look at the model's results on some sample images. So let's test out our model with some images from the predefined test dataset of 10,000 images. And we begin by recreating the test dataset with the two tensor transform included. So here is a sample image from the dataset. So as expected, it has a size 1 by 28 by 28 tensor, and this is the image, and it has a right label 7. So let's define a helper function predict image which returns the predicted label for a single image tensor. So first, we are passing in the image in the model. We call dot unsqueeze and pass in 0, and this simply adds another dimension at the beginning of the 1 by 28 by 28 tensor, so making it look like a 1 by 1 by 28 by 28 tensor, which the model views as one batch of data containing just a single image. Then we pass it through the model, and then we use torch.max to simply get back the prediction for the batch. And in this case, since there's only one element in the batch, we pick out the first element and return it. So let's try this out with a few images. This is once again the same image. The label and the prediction are both 7. Here again, the label is 0 and the prediction is 0. Similarly, this is it's not very clear that it's a 9, but the model does a good job at it. And the same here as well, right? So identifying where our model performs poorly can actually help us improve the model. And if we try for a few more examples, we're quite likely to run into some examples where the model fails. And we can then improve the model by collecting more training data, or by increasing or decreasing the complexity of the model, maybe training for a slightly longer time, and even changing the hyperparameters, right? So as a final step, let's also look at the overall loss and accuracy of the model on the test set. So we create a data loader using the test dataset, and then we pass it into the evaluate function. So we expect this accuracy 84.8% to be similar to the accuracy or loss on the validation set, which happens to be the case here. If not, we might need a better validation set that has a similar data and distribution as the test set. And the test set often comes from the real world data, and that is where the performance of our model really matters. Right. And now, since we've trained our model for a long time and achieved a reasonable accuracy, it would be a good idea to save the weights and the bias matrices to disk so that we can reuse the model later and avoid retraining from scratch. And here's how you can save the model. So we call torch.save, to which we pass model.stateDict, and then we pass a path or a file name where we want to save the model. It is a convention to save models under the .pth file name extension. So once we run this, the model is saved, and then the .stateDict of the model method inside the model, this returns the ordered dict containing all the weights and bias matrices mapped to the right attributes of the model. So let's take a look at the stateDict. As you can see here, we have linear, which corresponds to self.linear, and then it has a .weight and a .bias matrix. Now to load the model weights, we can instantiate a new object of the class MNIST model and then use the load_stateDict method. So here we instantiate MNIST model into model 2, and then we call .load_stateDict. Into it we pass torch.load, which loads the information inside the mnistlogistic.pth file. Right. And as you can see here, the model 2 now has the same stateDict with the same values inside it. Now, just as a sanity check, let's verify that this model has the same loss and accuracy on the test set as before. And as you can see, these are the exact same values. Now, as a final step, we can save and commit our work using the Jovian library. So first I import Jovian and then I run jovian.commit. So this saves the notebook and it uploads the notebook, it captures the environment and it creates a commit. So now I get the same notebook hosted online at this link, which I can share with anybody and anybody can reproduce this. The Jovian notebook also captures the Python environment automatically, which makes it easy to reproduce the work using the Jovian clone command. And Jovian also includes a powerful commenting interface so that you and others can discuss and comment on specific parts of your notebook. So we've created a fairly sophisticated training and evaluation pipeline in this tutorial, and here is a list of the topics that we've covered. So we started out by looking at how to work with images in PyTorch using the MNIST dataset. We also worked on splitting the dataset into training and validation and test datasets. We created PyTorch models with custom logic by extending the nn.module class. We interpreted the model outputs as probabilities for classification using softmax, and then we picked the predicted labels by looking at the highest probability. Now we picked a good evaluation metric and a loss function, so which are accuracy and cross entropy in this case for classification problems. We also set up a training loop that evaluates the model using the validation set at the end of every epoch. Then we tested the model manually using randomly picked examples from the testing dataset. And finally, we saved and loaded the model checkpoints to avoid retraining from scratch. Right? So there is a lot of scope to experiment here, and I encourage you to use the interactive nature of Jupyter to play around with the various parameters. And here are just a few ideas to get you started. So try making the validation set smaller or larger and see how it affects the model. Or try changing the learning rate and see if you can achieve the same accuracy in fewer epochs. Or try changing the batch size. What happens if you use too high a batch size or too low a batch size? Or try modifying the fit function to also track the overall loss and accuracy on the training set and see how it compares with the validation loss and accuracy. Can you explain why it's lower or higher? Try training with a small subset of data instead of the entire dataset and see if you can reach a similar level of accuracy. Then try building a model for a different dataset such as the CIFAR 10 or CIFAR 100 datasets. And then there are a bunch of other things that you can think of and try. And here are some references for further reading. So for a more mathematical treatment, you can see the popular machine learning course on Coursera and the discussion there on logistic regression. And the training loop defined in this notebook was inspired from the FastAI development notebooks, which contain a wealth of other useful information that you can check out if you read and understand the code here. And then for a deep dive into softmax and cross entropy, there are a great number of resources online, but this is one I would recommend. So with this, we complete our discussion of logistic regression and we are ready to move on to the next topic, just feed forward neural networks.